Jai Hind everyone. I am Kajal Kaushal, Assistant Professor in the Department of IT in Ajay Kumar Garg Engineering College, and here I am to present the topic of addressing modes in computer organization and architecture. This is a very important topic in terms of various competitive exams as well as the university exams. So first of all, we need to understand that what exactly do we mean by the addressing modes. So addressing modes, as we have already seen, there are various type of instructions formats. Instruction formats are carrying the op mode, are carrying the opcode, and also are carrying the operand as well as its location as well. Many a times the operands are being given and many a times its location is being given. But the point is that how will that particular operand be fetched out from that particular instruction? So for that, depending upon the computer architecture as in its von Neumann, its Harvard, whatever the type of architecture, there are various addressing modes. And all those addressing modes decides as to how the operand will be fetched from either the memory or the register, or it can be there in the instruction as well. So overall, it's the execution of the instruction, is the CPU design that plays what type of addressing mode are we dependent upon. Moreover, this addressing mode also helps to optimize the code, and it also helps us understand the machine level programming. So as we can see here, there is the instruction. This instruction consists of the operand, and this operand can either be present directly in the instruction or it can be there in a separate part, whether it can be in the memory or it can be in any of the register, and that particular address will be given in the instruction format as to what type of instruction format are we considering. So our main objective of this video lecture is that we are going to understand all the different addressing modes, and we are going to learn how the data and the instructions will be accessed, and also how it will be manipulated as well. Moreover, we need to understand why do we have different type of addressing modes. So it's all because each and every addressing modes are having their own sort of advantages and disadvantages. So depending upon the type of depending upon the situation, depending upon our need, depending upon the need of the program type, the program execution, the selection of addressing mode is being done. So these are the various types of addressing modes. It can be immediate, direct, indirect. Here we can see there are two things, direct and indirect. Direct as in we can get the operand no matter where it is there, where it is being stored, we can just fetch our operand directly. And indirectly means we need to follow certain path. That path can be calculated by the various situation, by the various formulas that we will understand in the coming slides. Whether it is register, whether it is register indirect, it is being addressed by having some initial value in the index register, or it is having the value in some base register, or it's the instruction only that is having the operand. That's the case of the implied, where the operand can be implicitly given or it can be explicitly given in the immediate addressing. Moreover, many a times our register count, the register value is being driven by the initial value of the effective address. Once the effective address is calculated, the register value can move upside down or it can move upwards. So that's the case of auto increment and auto decrement mode. We will see it in the coming slides. The very first addressing mode is the immediate addressing mode. In the immediate addressing mode, the operand is explicitly given in the instruction itself. That explicit means we can immediately get the operand directly in the instruction. For example, let's consider this instruction. This is the instruction which is saying the data, the value is to be moved to the accumulator. The data is to be moved to the accumulator, and that value will be directly fetched from the instruction only. So that means this hashtag identifies it as the operand itself. This value is the operand itself, and this value will be entering in the accumulator. This value 5, the operand value, will be entering inside the accumulator. The accumulator will be filled by the value 5. That means its effective address need not be calculated, as the data is already embedded inside the instruction. It is very simple, very quick, but there's a disadvantage. Is only related to small constants. We can't give a bulk amount of data in the instruction set because of the constraint that we are having. We are having op mode, then we are having the opcode as to what we need to perform, and then we are giving the operand. This instruction set is having a predefined register information in terms of bits. Let's say it's of 16 bits, or then we need to be restricted to the operand size. We can't take more than the required amount of the bits that's being already defined. So in this way, we can just have some operand inside it, and that should be explicitly given. So whenever we need a small constant that needs to be given, for example, the constant value in a program is 4, then every time the 4 will be fetched from the instruction itself. We need not calculate the effective addressing. Second is the direct addressing mode. In the direct addressing mode, we can get the effective address directly from the instruction. Mind it, earlier it was the operand. Now it's not the operand. Now it's the value of the address. It's the address itself. For example, here in this case, move towards what's being done. It's moving some data from the instruction value to the accumulator. And what is being moved? The value whichever is stored at the location 5000 hexadecimal in terms of hex, 500H, that value will be brought inside the accumulator, that is the CPU register, that is the accumulator. So here the instruction is being there. Address of the operand. In the instruction, address of the operand is there, and from that address, we can locate, we can bring our operand from that location and will execute the whatever process was being done. And then second example, there's loading of the operand from the location 2500H, and that particular value is being defined in terms of the register transfer language. We always refer to it as M in square brackets, the address, the value of the address. So here that particular address is having some value, and that operand value will enter inside the accumulator. So it requires the memory access. Earlier, in the immediate, the memory access was not required, but now the processor needs to address the memory as well. This processor will reach to the memory, and in that memory, wherever the location 2500H is there, it will bring this operand for the execution. It will fetch this operand from this particular location and will execute the instruction. So here we can say the advantage is that it's quite easy to understand, it's very good to implement faster, but it has again a limited address space. Whatever the value of the operand is there, we are restricted by the amount of memory it's having, the amount of memory it is being given, assigned. So that memory is just playing a restriction in our instruction operand. We can store that particular operand in the limited amount of memory that is being given for the instruction. In the indirect addressing mode, here we can think it of as some type of, let's say there is a pointer and it's having the address of a particular register, or we can say a memory, or we can say an operand. So that's the address, containing the address of an address. So in this type of addressing mode, the instruction specifies a memory location that holds the address of the operand. Okay, so there is one memory location. From that memory location, we reach to the another, and from that particular final destination, we can fetch the operand. Now, let's take an example, move A 5000H. Here what happens, this particular value is having an address of, suppose this is the location 5000H and it's having a value 2005H. Then this 2005H, whatever it is containing, let's say it's containing the value 55 or 550. This the operand, this is the final operand, but we have reached to this destination via this path. So it's containing the address of an address, and that is finally having the operand value. So we can say that effective address is being calculated by the HL pair, that is higher and lower order byte pair. The address is always being given in terms of this. If H value here for our example where we consider 2005H, we can say this was the H 20H and this was the L 05H. So it just made a pair of HL, that is the high and low order pair of the bytes, which gave us the value of the address that is containing the operand. So data flow is somewhat like this. The memory is having the address in HL, which is having the value of the accumulator. That's given to the accumulator. So we can say earlier we required just one memory access, but now two memory accesses are being required, one for the address and one for the operand. One is containing the address and another is containing the operand. So, but even though the path is long, but there is a greater flexibility in accessing the memory. We can store a more amount of data. Earlier, we were restricted with the address space, but now we can store a more amount of data. And the disadvantage here is that due to the more access, double access of the memory, it is comparatively slower in compared to the initial addressing modes. Next is the register addressing mode. Here, the operand is stored in the CPU register. So, it's comparatively very fast because all the registers in the processor register organization, we have seen there is a stack of registers. So, in any register, that particular data will be stored. It will be easier for the processor to fetch that data from any of the location if there are multiple registers from R0 to we can say R7 if there are 8 registers and our operand is stored somewhere in this register, then that particular value can be easily brought for execution. So, here the register flow for our example move AB will be somewhat like that. The effective address is there in the register B, and that value, the value which is stored in the register, will be given to the A. So, effective address will be the register B, and the value whatever it is containing, that value B, value that is stored inside the register B, whatever value is being there, that will be our operand. The value that the register B is containing will be the operand, and the register B is our effective address. We need to calculate two things. We need to calculate effective address, and then we need to fetch the operand. So, here our effective address will be register B, and the value that it is having inside it is the operand value. It is again very fast and efficient because it's already there in our processor, but it's totally dependent upon how many registers are there. So, we are restricted with the number of registers the processor is having, the CPU is having inside. So, its disadvantage is limited by the number of registers. Next is the register indirect addressing mode. Again, it behaves like the indirect addressing. Here what happens? Again, we are having the same accumulator. A data has to be moved from somewhere to this particular accumulator, but here this R1, the R1 in our instruction, we can think it of as the memory location that refers to the memory at the address in again the HL pair. I have already explained this is HL pair, means the high and the low order byte of the address. This address is there inside the register R1. R1 is having a register value, an HL location. That HL location will give us the operand value. So, we are reaching towards the operand via this address. So, our register is having an address, and that particular address may be of another register. It may be of the memory location as well. It can be of any location. From there, we can bring the value to the register A or the accumulator that is being asked for in our instruction. Basically, it is used for accessing the arrays and the tables. We can access any index value of the array, and we can have a lookup table so that we can reach to any particular row and column value. So, advantages is again it's very flexible and efficient, and its disadvantage is that again this instead of getting the operand directly from the register, we are asked to move one level ahead, that is we are having a indirected path so that we can bring the operand. Then there is an index addressing mode. Here we can think it of as we are being given in the collection of registers, there is one index register, and that index register is the value of maybe the number of bytes that are being stored or the constant value, anything it could have, and that particular value is added to the base address, and this base address can be collected from the instruction only. Suppose we are having a 2-word instruction. Here we are having the opcode, we may be having the opcode, we may be having the op mode, and suppose here we are having the operand part. That could be the operand or that could be the address, anything it can be. So, here what happens, whatever value is here, be it the operand or the address, we can think it of as the address. This base address, this acts as the base address, and to this base address a constant value which is being stored in the index register is added to it, and from there the data is being accessed. This base register value and index register value together when added give us the effective address, and that effective address will help us locate the operand finally. So this is ideal for all the types of the data structures from where we can fetch our data. But overall, it increases the complexity of our instruction. We need to optimize more in our execution process, but here the complexity increases. Then is the relative addressing mode. Many a times, suppose we have 32 gigabytes of data, then from that value, we can think it of as, if we divide this as in terms of bits, we can divide it into 8 bits blocks. So we will be having, suppose we will be having somewhat words which are collectively referred to as in terms of byte addressable memory. I am talking of byte addressable memory. So in byte addressable memory, if we are having one word or two word each in terms of the byte, and suppose we are having a 4 byte value, each word is of having 4 byte, then our program counter must switch to the 4th location, or we can say the 5th location after counting the 4 bytes. 1, 2, 3, 4, it needs to jump to the 5th particular location. So we need to tell the program counter to reach to that location, because our memory is of 4 words and each word having the length of 1 byte. So it needs to calculate every time 4, it needs to add every time the 4 value to our address. So for that, if we start calculating line-wise sequentially, then it would be a very time-taking process. So for that, this relative addressing mode is quite helpful. What it does, it behaves, it takes this value, as the offset, and every time it adds the value 5 to our initial value and makes the program counter reaches to that particular location. So moreover, it helps in the branching examples. It helps in the program that are having multiple branches. It helps for the displacement, where we need to get to the target address after adding some value that is totally fixed depending upon the initial memory size that we have considered. Okay, so its advantage we can say is that it's totally position independent. Wherever the program counter is there, it just needs to add that value so that it can reach to the next instruction wherever it is being stored. It's every time add that value and reaches to the current location. So we can think it of the advantage, but again it is having a disadvantage because the range is limited. We can't move that value to anywhere in the location. We can't say that we are moving it to once it was inside the memory stack and again we are moving it to the register stack. No, it won't be possible. So it is inside the program jumping, program branching manner. It's helpful for the program branching. Base register addressing mode, it's somewhat like same as the index register. Here we are being given the base register, and that base register helps us in the modular programming approach, where there are multiple modules and we know that from one module we need to move to the next module and to the next, and every module is having a fixed set of value. So that value will refer to as the displacement. This displacement value is already in our operand section, operand or the address section of our instruction. Here we know there's one opcode and opmode also. From the operand or the address, this displacement value is being considered, and from here when it's added to the value of the base register, like here in our example, it was something has to be moved, some value has to be moved to this register. Here the base value base register value is being added to the current value. This current value, let's say, is being brought from this side, 2000H. It is added to the base register value. It will help us get the address of it will help us get the effective address, and from this effective address we can calculate a value, and that value will be moved to the register AX. Simply, it's just calculating the value of the operand or the address to the value of the base register, and from there we can get the value of the from there we can get the address of the memory location, and this memory location will help us get the value for the register that has to be moved to register AX. Again, it simplifies the memory management because things are already fixed. The base register is having a value that's fixed for the fixed throughout the program execution. The base register gives us the value. That value needs to be added to the displacement value. Displacement value is already given in the instruction set. So, we can easily calculate that. But it requires the thorough maintenance of the base register. We need to make sure that the base register is intact, it's having that value so that it can be added to it. In the implied addressing mode, it's very simple. Let's start with this part, advantage. It's the simplest of all because here the instruction itself is behaving as the operand. It's the instructions that is telling us what to do and how to proceed. For example, this CLC is to clear the carry flag. If the flag value was 1, that CLC implies that now it has to be converted to 0 or vice versa. If we are having the command CMA, that means it easily understandable that it is complementing the value of the accumulator. If the value of the accumulator was this, then it needs to be complemented to this or vice versa. That means the value here is the instruction itself. The instruction itself is implicitly telling what the instruction needs to do and how to proceed further. That means it doesn't require any effective address because the operand is fixed. Operand is very much fixed from beforehand. That the data flow is just like this. The register value is being given to the ALU, and that ALU itself does whatever it was intended and it's stored in the value of the register A. That means the register A takes into the consideration. Next is the auto increment or auto decrement mode. Here what happens, the indirect mode is such, it is very much similar to the indirect mode, but here the value of the content, the value of the register when given, when suppose we are having the value, let's say the register was having the value 700 or somewhat like this, then this value will be given to the for the calculation. This value will be given for the calculation, but if there is auto increment, that means after the calculation is being done, this value will be automatically incremented to 701 so that it will be pointing to the next instruction in consequence, in a sequence order. And whereas the auto decrement mode suggests us to first of all decrease the value. It has to be decreased, that means it will become 699 and then only the value is being executed. So in auto increment, first the execution is being done, then the register value is being incremented. In auto decrement, first of all the value is decremented, value of the register is decremented, and then the execution is being done. These all addressing modes are comparatively different to each other, different with each other as per the requirement. Some are fast, some are having a 1 memory access, some are having the 2 memory access, and some are fastest within the CPU, good for arrays, looping, depending upon the various situation I have already explained. So, in summary, we can say the addressing modes defines how the data is being accessed by the instruction. Okay, how we can get that data. So, there is a trade-off again. If we want speed, or if we want flexibility, or if we want simplicity, all the things cannot be achieved at a time. We need to switch to something that is more of our need. If we want the speed, then we can select some register mode. If we want the flexibility, then we can select the implied or whatever. So depending upon our need. It can be understandable by seeing this example. I have an example already being done for you. So here is the memory. We can think it of as a two-word address. It's having two-word location. One word at the 200 location. The second word is at the 201 location. So this way we can say that our address is of two words. It's having the two-word access of our memory stack. Okay, there is a program counter, a register, a base register, or we can say the index register, and there is the accumulator also. Here, if we want to calculate the effective address depending upon the mode that are being asked, then how can we calculate? Let me explain to you. If we want the direct address, so what was there in the direct address? Direct address was having the value of the address of the operand. So what's the value here? It is having the value 500. So 500 is what? 500 is the location where the operand is the location from where the operand will be brought. So 500 will be the effective address, and this 500 will be given to the accumulator as the address. Likewise, this, it is having the memory word. We need to read this memory word from the location 500. So what's there inside 500? It's having 800. So content of accumulator will be 800. In the immediate operand, we know that explicitly we are having the content that has to be given to the accumulator. So there's no need of effective address. Only the value of the operand, that is the 500, will be brought here in the accumulator itself. It is explicitly decided. In the indirect address, what is there? The value, it's kind of memory word that has to be read from the memory location, and then that word will be read. Twice access of the memory. So what's there? The effective address. How can we calculate the effective address? The value was 500. When we move to 500, we got the value 800. This value will behave as the effective address, and this effective address will be having the value as 300. Like here, 800 is having the value 300. Then is the relative address. Relative address, that I have already explained. What it does, it adds up to the program counter. So the instruction need not move again and again. It's already having the instruction that it can be moved to the next location the program counter is pointing to. So the program counter was having the value 200, and our next instruction will be where? The next instruction that started from 200 will be 202. So 202 will be added to the value of the address, that is 500. So it will point after this 202, it will naturally point to 202 plus 500. That means it will point to 702. So 702 was containing 325. So 702 will be the effective address. I hope it's clear to you. What it has done, it has first of all considered the next instruction from 200, because it was a two-word instruction, and then it added the value and then calculated the effective address. From this effective address, the content of accumulator was calculated. In the index register, what we know, we are having a index register value. This index register value is constantly being added to the value given here. So index register is having the value 100. This 100 will be added to 500, which will give us 600. 600 will behave as the effective address, and this effective address will be searched for in the memory stack. This is here, and this value is 900. So the content that will be added to the accumulator is 900. The register address, we know that it's the register itself that is containing the value. So register address, that means if the mode of address is register, that means we need to move to the register itself. So register value is 400. So automatically the accumulator will not calculate any effective address. It will just consider the value that is stored in the register only, and that value is 400. Just by observing that it's the register addressing mode. In the register indirect, whatever value the register was having, now it behaves as the memory. So it is the address itself. So that means this behaves as the address for the operand. So that means 400 needs to be searched for, and since 400 location contains 700, so this register indirect will move us to the content 700. In auto increment and auto decrement, I already explained what happens. The value is first calculated. The value was 400 in the register. First the value is being calculated. So 400 contains the value 700. First of all, it will be calculated. 700 will be brought for the instruction execution, and afterwards this register value will be incremented. So this value will now be 401 if auto increment addressing mode is being used. But in case of auto decrement, first of all, the register value will be decremented. So this register value will be decremented to 399, and then whatever value is stored at the decremented value of the register, that is 399, we will search for this. 399 is having 400 value. Since 399 is having 400 value, so this 399 is, 399 is having 450 value. So this 450 value will be brought to the accumulator. This will be the content for the accumulator. So this was the example to explain the addressing mode in detail. I hope it was understandable. For any query, do comment below and ask to clear your doubts. Thank you so much. Jai Hind.